Just so you're aware, I am recording this class. If your sound is not off, you're going to hear an echo. So you need to make sure to turn your sound off on your device. Right now, I'm using my laptop as a microphone because in my experience, I've been doing this for several years. It's very clear. I purchased a different microphone that's USB. I haven't perfected it yet, so I'm still going to be using my laptop as a microphone. And so what we're going to do is we are going to go over the first lesson. This lesson actually has two parts. We're not going to finish everything today. Measurements is actually a very large topic. And in working in a science lab, you have to know how to measure properly. So that's why in the introduction to chemistry, the first place we're going to start is with measurements. Today we're going to cover a couple of topics. What we're going to cover is percent error. You may or may not be familiar with it. This has to do with the ideas of accuracy and precision. And we're going to cover an idea called significant figures in measurements. Significant figures maybe nobody is aware of up until this point. That might be brand new to you. And so you'll see that I have some devices measuring utilities out, and that's to help us understand what's going on in that topic. So we'll be doing a few demonstrations today throughout the lesson. You will need to take notes on this lesson. Just to be clear, I will be posting these notes after school today along with the recorded lesson. So for any student who's missing one of my pre-AICE classes for this lesson, or if you find you need to go back and hear something re-explained, it will be posted on the Google Classroom after school today. And so I just wanted to be clear about that. And this is the class, once again, that is being recorded. So you are now being recorded, meaning if you say something, it will be recorded. All right, so let's go ahead and begin. Unit 1, Lesson 1, measurements. And I will turn the recording off when we go to lunch and come back, by the way, so you'll have a few minutes to settle back in. But right now it's being recorded. All right, let's get started. The expectation for notes is you write the title and then all key terms, bolded and underlined, you need to write those down in your notes. And all practice examples, you need to write those down in your notes as well. We are going to be starting with some math. So if you do have your scientific calculator, you will want to take it out. So I would like you to take a moment, take out your scientific calculator. If you do not yet have a scientific calculator, you've got a couple options. First, raise your hand and I'll work from the front. Oh my goodness. I will not be able to provide you all with a scientific calculator today. But there is another option. Except for this one, starting with the front. You have? Okay. You've got the last one. All right, so if you do not have a scientific calculator, what I'm going to do is on Google Classroom, I'm going to post the link to the Desmos scientific calculator. You can access a scientific calculator on the internet. You will not be able to use that scientific calculator for a quiz or a test, but you could use it for classwork, homework, and for what we do in class together, like today. So right now I'm going to period 4, and I am posting the link to the Desmos scientific calculator. So if you did not have a scientific calculator today, you need to have a tab open to the Desmos scientific calculator. You may want to bookmark that tab because you're going to need it often. Anytime you forget your own scientific calculator, you're going to need that. But on the day of your first quiz, you're going to need to have your own calculator by that day, which is probably just a couple weeks from now. So make sure on the materials list, you are getting a proper calculator. All right, so going back to begin the lesson. All right, so first, bold and underline definition is what is a measurement? That's what the lesson's about. So anytime you see something that's bold and underlined, this is a definition you need to know. You need to write it down in its entirety. A measurement is some kind of number you're given that is not only a number, it also includes a unit. You will be doing a lot of measuring in this class. If I just tell you the number 29, I'm going to say, it's 29. It's 29. You would say, it's 29 what? What do you mean it's 29? Huh? Well, it's been 29 minutes since class began. That's what I meant by 29. Every number in this class is going to have some meaning associated with it, whether we're talking about an atom, we're talking about a molecule, we're talking about something else of mass. We have to associate every number in this class with a meaning. I believe I told you last class that chemistry is half a math class. Half of the time, you're going to be working through math concepts. Half of the time, you're going to be working not through math concepts. But there's always some element of adding or subtracting numbers. We work with a lot of numbers in this class. Actually, analytical chemistry, which is one of the main branches we'll discuss in the next week or so, is a whole entire branch of chemistry that is devoted to determining how much quantity you have of something. For example, in your water, what is in your water? Is there chlorine in your water? Is there lead in your water? Hopefully not. Is there sulfur in your water? Knowing those concentrations, that's actually a whole entire branch of chemistry is dedicated just solely to that. It's called analytical chemistry. So we work a lot with amounts in this class. And the other thing that we work with is trying to figure out what we have, figuring out the identities of an element, an ion, a compound. And if you don't know what any of that means yet, you will shortly. But for now, measurement. Quantity that has both a number and a unit. So before we move forward, I just want to bring up real quick, there are some units of measurement that are lab equipment that we use. So the units of measurement we use in lab. You're going to want to write this down. This is for mass, for volume, for time. When you report your values, in what units do we use? So this is not necessarily metric system or standard international. This is just what does our equipment report? And that's where we're going to start because we're going to have a measurements lab. As I said, if we can get this done today, we should be able to have a measurements lab next week. So units of measurement we use in the lab. For mass, what do you think we measure mass in science? Go ahead. Grams. So all of the balances, and we'll be working with them later today, we should always make sure that our readout is in grams. And so mass is in grams. Volume. Our next one is volume. When we measure volume, what is the unit? And there's actually two that are equivalent to each other. I'm going to tell you both of them because someone brought it up in the last class. Go ahead, one of them. If you want a clue, the cylinder in front of you actually has it listed. Go ahead.
Milliliters?
Milliliters. Milliliters, or the equivalent to milliliters in international units is actually centimeters cubed. Milliliters and centimeters cubed are the same unit, actually. Milliliters, what's printed on all American devices. So that's what you'll see in a lab, but it actually is the same as centimeters cubed. Let's talk about length. When we measure length, we're going to have a ruler typically. Do we use the centimeters or do we use the inches side of a ruler for measuring length? Go ahead. Centimeters, because it's a metric system. So we would be measuring and reporting on our values in centimeters. We've got two more. Time. We can measure time. How much time passes?
Seconds.
Correct. When we report time, and we would do this when we're looking at a rate. How much time does it take for this reaction to take place? We report time in seconds, and that's what Cambridge expects as well, is that it's reported in seconds, not minutes, not hours, not days, seconds. And so the final one is temperature. How do we report temperature in the science lab? Go ahead. Celsius. There are other temperature scales. The one that most people here are familiar with is Fahrenheit. That's how in America we report the weather. But in science, we use Celsius. We also use another unit called Kelvin. Some of you may be familiar with, but Kelvin is not really seen until the ACE level of study because we use it for specific certain formulas for calculations. Celsius is the one you're going to see reported most often. And so just be aware when you're looking at a thermometer, the thermometer has two scales printed on it. One is Fahrenheit, one is Celsius, and the one we're going to report all of our values in is Celsius. So this is just to help prepare you for our first lab. How do we report our answers? And so make sure you have this written down so you can go back to it and review before we have our first lab next week. All right, so that's the first thing. I do want to bring up that I do like to pause a little bit before moving from one slide to the next. And I will give you a 20-second warning that I'm moving forward. This is to give you the ability, if you're just finishing writing something down, to write it down real quick. Or you can take a picture of what I have written if you need to catch up with what we're doing. So once again, now we are in a 20-second warning. I'm about to move forward. The expectation is, though, that you are taking notes on what I teach, because everything that I test is going to be off of what I teach, which is in the in-class presentation. And there is a grade for notes. All right, here we go. Your next set of definitions. So this is the part you have to write down, just the part that's in the boxes. Our next set of definitions is the definitions for accuracy and precision. This may be reviewed for many of you, but you should have it down just to know this is what's expected of you. And I'm also going to bring up, where does this apply into our actual class? I'll give you some time to write it down first, and then what we'll do is I'll show you some examples. This apply in the chemistry. Are you done? Accuracy is how close a measurement is to the true value, whereas precision generally means how close, if you take a bunch of measurements, how close those measurements are to one another. We can also talk about precision in equipment and precision in measurements, which we will now. It is established that the boiling point of pure water is 100 degrees Celsius. Let's say that you did an experiment and you found that the boiling point of water was 85 degrees Celsius in your experiment. Boiling point of water experimentally determined to be 85 degrees Celsius. Are you very accurate? Is that very close to 100? And there could be many reasons why your value's off, and when we get to a lab, we'll go over error analysis. But that's definitely not very accurate. Let's say another student ran the experiment, and they got that the boiling point of water was 35 degrees Celsius. Are they off? Are they off significantly more than you? Okay, so not very accurate at all. Let's say you measured the boiling point of water a second time, you got 87. A third time, you got 86. Are your values precise to each other?
Yeah.
Yeah. But are they still kind of far off from the right answer? Yeah, so precise but not very accurate. That probably means there's some systematic error, meaning that the same mistake keeps getting made over and over again, or the device you're working with is faulty. Could actually be another systematic error. So 35 degrees Celsius. Let's say that the other student was like, oh boy, that's rough. Let me do that again with some better equipment. And they get 35.00 degrees Celsius. Are they more accurate than they were before? It's okay. They're not more accurate, but is their measurement reported to greater precision?
Yes.
Yes. So that really is the difference in chemistry between precision and accuracy. Accuracy is how close you get to what you're supposed to get. If you're supposed to get 100 and you get 99, yay, that's not bad. And precision is how many digits you're using in representing your answers. So we care in this class both about accuracy and we care about preciseness. In a perfect world, your work would be both precise and accurate. That's what we're looking for, both precision and accuracy. All right, so just as a definition, some things you got to know going into the class. Now, how are we going to apply this? We're actually going to be, when you do your experiment next week, you're going to be calculating your error. One of the first things you're going to do is you're going to establish some information about an element or a compound, and then you're going to calculate the error compared to what it's supposed to be and analyze why that might be so. And so there's going to be two formulas now that are about to come up on the board. You need to write both of them down. Just so we're clear, in this class, you have to memorize everything I teach. That means any formulas that I went over, you have to memorize them. Any rules that I teach, you have to memorize them. If you were to take a Cambridge exam, they expect you know everything, and the only thing they give you is a periodic table. So although I'm not teaching you college level material, I'm teaching you high school level material. The way we prepare, one of the ways we prepare for the expectations of what would be at an ACE level of study and whatever science you take, chemistry, environmental science, marine science, is you have to memorize everything. And so you will not get formula sheets in this class, just to be clear. Everything that we go over, you have to know. Here are the two formulas. So write them down, and you also need to memorize them. And you'll memorize them hopefully through practice. You'll receive some practice today after we do practice examples, and you will get to work through these again in the Bell Work Kits class. So in order to establish what's called error, you have to know the following formula. Error is the measurement you took subtracted with what is considered to be the true value or the accepted value. Another way of thinking about error is how far off the measurement is from what it's supposed to be. So that's just to help you understand what is error. What are we talking about? When we talk about error, we're talking about how wrong the data is in comparison to what it's supposed to be. So I'm going to pause to give you some time to write the formula, and then I'll explain percent error a little bit more. And we'll go back to our boiling water example to see if we can calculate the error and the percent error there.
In the equation, what does it mean measurement? Like error equals measurement?
So if you measure something is 1.80 grams, you would put 1.80 grams there. And if it was supposed to be 2 grams, then you put 2 grams here.
Oh.
So the measurement is what you get in the experiment. So if you want to point to that, it's what you get in the experiment. That is what we call the measurement in this formula. And the accepted value is what is known to be true. What has been established, there's a textbook value for it. Millions of people or thousands of people have verified that this is true. So the accepted value, for example, the boiling point of water, it is well known that pure water has a boiling point of 100 degrees Celsius. It's been tested, it's been verified. So the accepted value is what is known to be true. or what is known to be accurate. So if we go back to our boiling water example, and we know the boiling point of water is supposed to be 100, right? And you got experimentally 85. That was what we said before. What is our error? Go ahead.
15.
It's 15. And it's technically negative 15. However, it technically also doesn't matter whether you write positive 15 or negative 15 because of what you see afterwards. So technically, if we follow this exactly, it would be 85 minus 100, which is negative 15. I don't express my answers like that. I just say the error is 15. I was off by 15. That's my error. And so 15 degrees Celsius, that's the error. What's the percent error then? Formula 2. This is how far you're off from the true answer represented as a percentage. And so we would calculate that by taking, hey, what's that right there? I've been asking every class. The absolute value of the error. And all that means is that whatever error you get, you have to change it to a positive value. You divide that by what the answer is supposed to be, and you multiply by 100. Whenever you see a fraction bar here, and I am so sorry, if you hate fractions in math, we are going to be working with fractions in a lot of formulas this year. Yes?
15% error?
Correct. If you see this line here, it means divide. The way you read it is divide. Use a calculator. You don't have to do it all in your head. If the numbers are easy, you may be able to, but you will be working with decimals as well in this class. All right, so let's take a look at our example again and see if we can calculate this percent error. I know you already have. The error was negative 15, but the absolute value of that error would actually be positive 15. So you would put negative 15 like that. The accepted value is what the boiling point was supposed to be. The accepted value is 100. These numbers are pretty easy to work with because you're both dividing and multiplying by 100. It just works out that way. And so the actual math operation you do is 15 divide by 100, because of this right here. This is divide. And then multiply by 100. Some of you will be aware that this should automatically cancel. And that your answer is just 15. But do we say 15 or do we say 15
Percent?
15%. Because when you write a percent error, your answer will always be in percentage form. You're literally just changing a fraction to a decimal in this formula. 0 by 15%. In the lab that we do next week, when you calculate percent error, I've seen students in the past have errors as little as 3% or 0%. And that's really good. If you get a percent error that low, that is fantastic. You have great technique. I've also seen errors of 300%. I have. And although I won't count it against you because we're just, we're learning technique, we're beginning the study of chemistry, it just means that something went gravely wrong in the process. And so we look at percentage errors and it tells us pretty much how good your technique is, how good your devices are, how close you were to what you were supposed to get. Most science, like advanced sciences, you would want a percent error as low as possible. You would want it under 10% typically. That's what's considered to be pretty good. And less than 5%, excellent percent error. Just to give you an idea. Over 50% error, rough. It's starting to get rough. But like I said, when you do this next week and you do calculate your percent error, if you get 300%, you got 300%. We have to be able to analyze why that happened. How did that happen? Where did the error occur? In Cambridge, if you were to take a lab paper from Cambridge, part of the grade is actually error analysis, analyzing if there was an error, how did it occur? What could be done to improve the experiment? And so there will always be some inherent error typically in an experiment. And like I said, next week you'll get to do an experiment where you calculate a percent error. All right. I do want to give you that little heads up that I am about to move forward. We're going to do 2 practice questions. I think we'll have time for both before lunch. We'll take a break and then we'll do the other topic that we have to do. So, practice question number 1. Here we go. I would like you to write all practice questions in this class. You should write the questions and the answers. I'm going to pause now to give you some time to write the question. If you already feel comfortable with what I've explained so far in the formula, you can go ahead and start solving in advance with me. But I do like to pause to give you some time to write the question out and work ahead of me if you feel confident with what we're learning so far. This question you're told, the established amount of calories in a can of Coca-Cola is 140. You ran an experiment and you found in your experiment that there were 210 calories. Now, the 140 calories is an established value. So your experiment was off. What is your percent error? Just to be clear, before you find the percent error, you should always find the error. So if you're starting to work ahead of me, before you start calculating the percent error, you should find the error first. That's a place where students went wrong in the last class. So I'm going to write out the steps, and I typically do the first time I'm explaining something, and then the next time we do a second question, I'll go through it a little bit faster. Step 1 is to find the error in the measurement. I'll write the formula out, but you don't have to. Error equals measurement minus accepted value. Error equals measurement minus accepted value. What is our measurement? Our accepted value? Like what's true?
140.
These numbers may be simple to work with because they're whole numbers. And so if they are or not, you're allowed to use a calculator. Just to be clear, no calculator shame. No shaming for using a calculator in this class. You're always allowed. 70. I'm not testing your ability to do simple math. I'm testing your ability to solve problems. So 70. That's our error. And it's 70 calories, right? Step 2. This is where we need to find the percent error. So what we're going to do now is we're going to use that formula. The percent error formula is the absolute value of the error divided by the accepted value multiplied by 100. The absolute value of your error, and you just need to remember your error is always going to be positive. 70. So we get 70 divided by the accepted value, 140, and then multiplied by 100. The mathematical operations are 70 divided by 140 multiplied by 100. 70 divided by 140 times 100. If you get this right, you should have gotten that it's 50%. That's pretty far off. To give you some context, if you were to overestimate the amount of calories in a Coke by 70 calories, right? There are 3,500 calories in a pound. Do 3,500 divided by 70 real quick. 3,500 divided by 70.
50.
So every 50 cans of soda, you would be off by 1 pound of body mass. That's what that would mean. That's what that would indicate. So pretty far off, actually. All right, I'm going to hold to give you time to finish writing the step, and then we're going to go to our second example. I told you we were going to do 2 examples before lunch, and then that actually is an excellent stopping point to go to lunch because we'll start the next topic when we come back. That's where we're going to use the scale and the cylinder that I provided at your table. Practice question number 2. I'm going to give you some time to write it down. Don't be scared of decimals. We're going to use them all the time in this class, but we always have a calculator, so don't stress. You can work ahead of me if you feel confident based on what we've done so far. And if you prefer to wait for me to solve, you can also wait. Just make sure to write down the practice question. I would always work ahead of my teacher in both my math classes and my chemistry classes and solve the problems as soon as I saw the formula to see if I knew how to use it or not. And that way, if I got confused somewhere, I could ask a question as it was being taught. And every once in a while, if I got really lucky, I would be able to figure something out that the professor did wrong. Every once in a while. But usually it was to catch myself in a question that you only realize you have if you try the question yourself. So remember, before we find the percent error, we have to find the error in the measurement. So step 1 is always to find the error. So I'm just going to write a little 1 next to it this time. 1, error. To find the error, you need to subtract the 2 values you're given. The one that you got in the experiment and the one that is supposed to be the true answer. And so what you got in the experiment is 2.850. And the one you were supposed to get was 2.699. So this comes up with 0.151 grams centimeter cubed. Now, because you're the last class, to get this lesson, and you typically will be because A days come before B days. So I'll teach this class the lesson last. Why this class and not 6th period? My 6th period is actually a different course. I teach the college level class in 6th period. That is actually the appropriate rounding. And I'll tell you why in a moment. That is the appropriate rounding. Your calculator actually gives you much more numbers than that. And so one of the things we're going to have to learn early on in this class, which is why we're covering this topic first, is we have to figure out where to round. Because I don't want you to write 10 numbers that your calculator gives you, and you don't want to write that out. So you have to figure out how to round appropriately. So we have this. One of the things that was asked of me in the last class that I want to bring to your thoughts is a student asked, why write that 0? Aren't 2.85 and 2.850 the same thing? It's a good question to entertain right now. Are they the same thing? Are 2.85 and 2.850 the same thing? If you think with your math hat, you would say yes. But if you think from a measurements perspective, they're not. And I'll be explaining why in the second half of the lesson. So yeah, that 0 actually is written there on purpose and important. It is a significant part of the measurement. You don't understand why yet? It's fine. I'm just letting you know it is written there on purpose. So you've got this as your error. To find your percent error, you would now do, this time I'm going a little bit faster. I put my error on the top, 0.151. On the bottom, I put my actual, what I'm supposed to get, which is 2.699, and I multiply by 100. I do those operations in my calculator, 0.151 divided by 2.699 multiplied by 100. And you should notice that when you plug this into your calculator, whether you use a scientific calculator or you use the Desmos as a tab on your computer, your calculator gives you 5.594664691. How do we know where to round to this? I haven't taught it yet, like how to round properly. So where would you round this to? A lot of you are intuitively correct.
The
Yes.
hundred?
What was yours?
Hundreds or thousands?
So actually, generally, those are accepted. There's actually a reason it is 5.59. So if you wrote 5.59, that was the correct place to cut it off. Until I fully teach it, you can always remember, as long as you write 3 numbers, it's usually going to be the correct answer. But to be clear on why, just for you who want the heads up in advance before I officially teach it, if you look at these 2 values in the calculation, your input here is 3 values, and your input here is 4 values. What do I mean by that? The 1 and the 5 and the 1, they're all separate digits. 3 digits here and 4 digits here. You always round to the lowest amount of digits when multiplying or dividing, so you would express your answer to 3 numbers. So 5.59% is actually quite accurate here. We're about to go to lunch, but I have a question for you because I think you can handle it. What would cause, outside of your own experimental error, what would cause the density of a material you measure to be different than what it's supposed to be? What do you think could cause the density to be different? Go ahead in the front.
Like a dust going in or something?
Wait, what?
Like a dust.
Okay, so dust. What else?
Could be a faulty balance.
Okay, faulty equipment, yes.
It may not actually prove amazing.
That's what I'm looking for. Yeah. So there are many factors. It could be your faulty equipment. I was saying outside of some kind of experimental error, what could it be? If you know you did everything properly and you still got something off, it is possible that the material itself is not, maybe it's not pure, right? Maybe there's some impurity there because different metals have different densities, which we'll learn about next week. But that's the idea. All right, we're heading to lunch. When we come back, we're going to go over significant figures. I'm turning the sound off. mute my mic at this point, and we're going to go ahead and start this topic. Now, I want to be clear here. You do not have to write everything on this slide. Only write the title. Only write the title. And I'm going to give you an instruction on something to do with your cylinder that has water in it in a moment. But go ahead and write the title. It says significant figures in measurement. Significant figures in measurement. And this is the second part of today's lesson. When you're done writing that title, at your table, you should see a graduated cylinder. I would like you to measure the volume of water in the cylinder, in your cylinder. Estimate to the best of your ability how much water is in that cylinder. So when you're done writing the title, look at your cylinder at your table. It has some water in it. Write down what you think the volume in your cylinder is. You don't all have the same amount, by the way. Read your cylinder and how much water you may have.
So it's like 0. Wait, this is 15. Wait. And this up to here is 1. So this is like 15. What? Oh, up here is 0.15? Oh, wait, no, there's 1. So it's 15.
When you measure volume, you read it from the bottom up. So that's how you count. So write down on your paper how much you think the volume is. And then you'll revise it in a little bit after I teach how to do it. But what do you think it is based on what you see in the syllabus? Is it exactly 16?
I told you it's 15. How's it going to be 10 to 20? It's 15.
Some
16.
Some different values going on.
I was asking.
16.5. Okay, write that down.
It needs to be double that. 0.5.
Write down what you think, and we're going to go over how to do this correctly very shortly. All right, so hopefully I've given you enough time. Go ahead and write down whatever value you think it is.
15 minutes.
And I'm going to show you another cylinder and teach you how to read it correctly. And if you need to revise what you did, we will do that after. And so it's okay right now if you didn't get it exactly correct. So how do we read the volume of water? Reading measurement tools. This, by the way, it's called a graduated cylinder because every single one of these lines are graduations. Every single one of these lines represents what amount of volume, and it's the same as the cylinders you have. Every line represents how many milliliters. What do you think? Every line represents how many milliliters?
Like 1.
1. So the first thing to recognize is that every line is 1 milliliter, right? So when we read the volume of water off of a cylinder, the next thing you need to know is where to read. You should always read at eye level. So if you're looking down at the cylinder or you're looking up at the cylinder, you may get an incorrect value. You need to look at eye level. So for example, if I see this cylinder here, I would want to make sure that my eye is matching the level of the water. So you always measure at eye level. So you're going to want to write that down too because it's going to go into your lab next week. Measure at eye level. Next.
What does it mean to measure by eye level?
That means that wherever the water is, you bring your eyes down to there and you read it straight to where the water is. You're going to see that I'm trying to find what's not a fancy word for this, but you're going to see there's a curve. There's a curve in the water. It curves down. The math term for this would be concave, I believe. You've heard of that, maybe? If not, not a big deal. The bottom of this curve has a fancy science name. It's called a meniscus. And so you're actually supposed to read at the bottom of the curve. So wherever you have the curved line, you're supposed to read at the bottom of that line. So then knowing that, and I'll change my color, I know that I have to read this here. So then the question is, how do I measure this volume? What would I report as my answer? And so do I have more or less than 40 milliliters of water in this example? More. Do I have more or less than 44? This is 1, this is 2, this is 3, this is 4. Less. So I know it's right around 43. Do you agree?
Yeah.
Right around 43. Appropriate answers is to say either 43. Now, question. I'm going to erase what I have written here because I want to show you something. So I'm erasing this. Is there a possibility you could have had a water level that was in between 43 and 44?
Yeah.
Was that a possibility?
Yeah. Yes.
If that happened, what would you have written as an answer?
0.5.
43.5. But that's not 43.5. This actually looks to me like it's resting pretty much on that line. So what would we say? 43?
43.0.
So when writing a measurement, you write all the numbers you know for sure, which is given to you by the lines here, and then one final digit you estimate. So it's all the numbers you know, and one that you estimate. One estimated value or digit. And this is how you read off of lab equipment properly. And so this would be 43.0. Now, what if you were like, I don't think that's exactly 0. I think it's right above 0. Instead of writing 43.0, what would you write?
Like 42.1.
And both of those are accepted. So when you write an answer for measuring, a couple things you need to do. First of all, you need to adjust at eye level. Then you need to read the bottom of the curve. And then you write all the numbers you know and you estimate one additional number. Now I have a question. In this measurement, is the 4 important? Yeah, because if it was 3, it'd be something completely different. It would be like here, not there. Is the 3 important?
Yeah.
Is the 0 important to tell me it's right on the line?
Yeah.
So every one of these numbers is what we call significant. And our second topic today is significant figures. So when we talk about a significant figure, a significant value, it's a value that's actually being measured. And so it matters in the measurement. And it sounds like a silly topic, but as we get into it, you'll see when values are significant versus when they're not significant in measurement. And that's why I have some of the tools here to help you understand. So we're going to get to the definition, but beforehand, look back at what you measured and see if you can make any corrections. You should measure now, measure your volume to the nearest 0.1. So if you had rounded to the whole number, now readjust it to measure it to the nearest 0.1. So what would it be?
Every big line is 1.
Remember, you look at it at eye level. And you measure to the nearest 0.1.
And look at the person down. So it's 14.1.
You can't estimate 2 numbers.
4.
So it's the halfway point, it's 11.5. Yes. Oh, just checking.
14. the curve.
Now we're going to go ahead and go over what is a significant figure.
No, that's like 14.1.
Write the definition. Write the definition for significant figures. I've already explained through demonstration what a significant figure is, but you need to have the formal definition. So go ahead and write it to the part in the box. You don't have to write everything in the slide, just the part in the box. So what we call a significant figure in our measurement is all of the numbers that we know and one digit that is being estimated. We call those all of the significant figures in a measurement. Those are the numbers that matter. You're like, how could a number not matter? Well, we'll talk about that in a little bit. And so the final thing we'll have to talk about is, well, how can we look at a measurement and know if the value that's being reported is one that is significant, that matters, or one that doesn't matter? And so for that measurement we just did with the cylinders, all of those numbers mattered because they were all part of the measurement that we took. There, believe it or not, are a lot of rules to determining if a measured value that's being reported to you, if it's significant or not. Most of the rules have to do with zero, whether the zero matters or not. Sometimes zero matters, sometimes it doesn't. We're going to address exactly when, why, and how zero matters. And so I'm giving you about a 15-second heads up that I am going to move forward shortly. Do remember that I am recording today's lesson, so if you do fall behind or you need to add in some information, anything is in the slides that I didn't tell you to write that you want to go back and read over, feel free. I will be posting that after school today. But you should be actively going through and writing the bold and underlined terms and practice problems as we go through the lesson. Alrighty, let's go ahead. So there's 6 rules to write, and you got to know them all. We're going to explain them all, and then we're going to look at some practice examples with them. And then you may have time, we'll see. You may have time to do your assignments in class, or at least part of what you need to do in class before we leave today. So here's the rules. And so you'll want to list them out, and you can write rule number 1. I did bold and underline each rule so you know what you need to write. You don't need to write everything in this slide once again. Just the bold and underline part is what you need to get, because these are the rules we're going to use to make decisions. The first rule is actually makes it seem like everything is significant. Rule number 1 says every digit that isn't 0 in a measurement is always going to be significant. We assume if someone wrote a number other than 0, that they wrote that with purpose because it was a measured number. So that means all numbers 1 through 9, or all digits 1 through 9, are always significant. If I tell you 32.5 miles, that matters. Every number matters. That's 1 through 9. I walked 16.5 miles last Saturday. It's approximately 40,000 steps. 16.5 miles. Yes, that extra half a mile mattered. It was a lot of walking. Every number 1 through 9 matters. So that means every other rule pretty much centers around whether a 0 matters or not, because that's the only digit that's not 1 through 9. So 0 is where it gets tricky. And so we're going to start to look at the rules for 0 shortly. I'm giving you a little bit more time here, 20 seconds before I move forward. Remember, you only have to write the rule, and then we're going to move on. You will see examples after we're done going through the rules. We'll go through some examples together. 2. Here we go. Rule 2 and rule 3 are here. All right, rule 2 and rule 3. We're starting to look at zeros. If a reported measurement has a 0 in the middle of other values, that 0 is important. An example is, let's say you have a very large dog, and maybe it's a Great Dane, very large dog, and you measure the weight of that dog, and you find that the dog is 105 pounds. Does that 0 matter?
Yeah.
Yeah, it's not a 1, 2, 3, 4, 5, 6. That was written with importance. That's part of the measurement. That dog is 105 pounds. So zeros in between other numbers always matter. They're always part of the measurement. And therefore they are significant. That's the way to understand it. So that's rule 2. That one's a pretty easy one to recognize. While you're writing these down, if you don't already have some ripped paper at your desk, I'm going to rip some paper.
Somebody did that.
Yeah, nobody got angry. This is for science. I'm ripping paper for science. If you don't already have ripped paper, I'm providing you with some because for rule 3, I'm going to explain it with an activity you can do. You have some? Would you like extra? Those are tiny. So. Have some. Paper. And I don't know if. Oh. All right, so while we're going to go through this rule, I want to teach you a little bit about your scale. We're going to use digital balances throughout the year. Please be kind to these. They did cost me $25 each. So they're not the most expensive scales, but they're also not the cheapest. I tried to make sure that there's a full class set so that we can use balances throughout the year. I also use them for the Cambridge examinations for those students taking the college level class. So please treat them with care. That's just a heads up. How do you turn on the scale? If it's not on, what you need to do is you need to press the red button. So look at your scale, press the red button. It's the on-off key until you see numbers. If you see 0.00, you're good. If you see any number besides that, you need to press tare. That's the middle button. That resets the balance so that anything you put on it will be the weight of that thing. So check your scale. Make sure it says 0.00 and at the top it says G at the top left-hand corner. If it says something else besides G, it means you need to change the mode back to grams. This is something that will happen. There's other classes that use the scales before you and they might accidentally change it to the wrong mode. So double check your scale and make sure it says G and 0.00. Now what I would like you to do is put your piece of paper on the scale. Place your piece of paper on the scale and see what it measures. This is the mass of your paper. The mass of your paper in grams. I've given you a very light piece of paper, so it should show less than 1. Make sure it says 0.00. If it doesn't, sometimes when you move it, it'll change. You press that middle button, and it'll reset it. So put a piece of paper on the scale and see what it measures. I'm going to put your names up on a wheel eventually. I was just waiting for all the rosters to finalize. But let me ask Alex Alexander in the front. What was your measured mass of paper?
0.75 grams.
0.75 grams. So that's a sample mass of paper. You should have gotten anywhere between 0.1, 0.8, somewhere in there. Depending on the size of the paper. Obviously, more paper has more mass. So I have a question for you. Now that you've all seen that number on the scale, is the 5 a measured number? Does the 5 matter? Is that part of the measurement?
Yes.
Is the 7 part of the measurement?
Yes.
Is the 0 part of the measurement?
No.
Yes.
Is this part of the paper? Is there part of the paper here that's 0?
Doesn't matter.
It don't matter. So that teaches us rule 3. Rule 3 is that zeros that are to the left of numbers are actually not part of the measurement. They're just there to hold the place. We call them placeholders. Actually, if we didn't write that 0 at all because of where it's at, it doesn't matter. Your math teacher might tell you different. But for the purposes of measurement, if I tell you 0.75 or I tell you 0.75, there's no difference. I've measured the same mass regardless. So it's just something important for you to note.
And if there was a 0, like, after the decimal point? Like,
That's a
double
great
the symbol?
question. Why don't you just take a little tiny piece of paper and see if you can get something like this? See if you can get 0.0 something on your scale. How much paper would that be?
That's so
Yeah, you can use it.
like this.
Got 0.06.
Okay, okay.
I got
You may have to recalibrate.
Yes, I got 0.08.
Oh.
Look at this.
You said what?
So look at this.
Now what?
Oh, I did it. 0.03. 4.
Point of a gram.
See if you can get something like 0.05. Like, see if you can make this number a 0. You'd have to take some more off, basically. You got it?
I got 0.05.
See if you can get around 0.05.
I did. Somehow we can.
You need to add some more. That's too much. You have to kind of adjust it until you have a 0 right after the decimal.
I got 0.05.
Perfect. Now, question, because it was the question that was asked of me. If you have 0.05, 0.06, 0.07 here, does this 5 matter? Is that part of the measurement of the paper?
Yes.
Is that 0 part of the measurement of the mass of the paper?
Yes.
Does the paper have a mass of a 0 there?
No.
No, not until you get this. You have to have double of this to change this to a 1 for it to be measuring the mass of the paper, right? So it's like that, just to give you the example. This teaches us zeros to the left of the first non-zero number. We call those zeros in the front. They're never significant. The answer is they're never significant. So never significant. They are not part of the measurement. Therefore, they're just there to hold how small or large the amount is. We know that 0.05 is a much smaller mass of paper than 0.75. And that extra 0 there tells us this is much smaller. We know that this is like 5/100ths, and this is to the 10th place. So this is definitely much larger than that. So it holds how small it is, but it's actually not part of the measurement of that paper. That paper doesn't have a mass of 0. 5 centigrams to be clear. If you don't know metric conversions, don't stress. That's a lesson for another day. Today I'm teaching significant figures. If you do remember physical science and you can do metric conversions quickly, you'll know. All right, we went over 3 rules so far. 1 rule of numbers 1 through 9, 2 rules with zeros. Can you believe there's 2 more rules with zeros? Oh my gosh. Zeros are strange. So you've really got to look at 0 very difficult. Like you're like, oh my gosh, what about this 0? What about that 0? Now we know if a 0 is in the middle of a measurement, it counts. It's part of the measurement. If a 0 is on the left-hand side, Doesn't count. Not part of the measurement. We call it not significant. So what other scenarios could there be? The next one. So this is rule 4. Rule 4. I'm going to ask you to do another activity on your scale to prove this rule. So the activity is see if you can add or take away paper until the balance reads a 0 at the end. So either 0.20, 0.30, 0.40. What I'm looking for is this 0 ending, but you have paper on the scale. So anything but 0.00. So add or take away paper until you see either 0.10, 0.20, 0.30 on your scale. That's the exercise that I'm asking for you to do. That proves this rule.
Oh, give me a tiny bit
See if
less.
you can try it.
Why?
Yeah.
Already
Take
got it.
out this one. We need 10 and 0.10. Yes, there we go. I got that.
Once you get it, just keep. Yeah, that's good. You got it.
Yeah.
You're welcome. Anybody need assistance? Anybody need to rebalance their scales? No, you're good. Still working on it. You're good. Good. Got it. Do you need help with working with your scale, or you got it? Make sure that you put enough paper so that the ending reads 0. So you can turn it on. And I want you to add or subtract paper until you see a 0 at the end here.
You always take this one back like nothing.
You have to add more paper. You just have to read
Oh,
0.
see? It does way wrong.
Maybe start here. You're good. Add it. And
Oh yeah.
okay, so you had to add or take away paper to get to that number. My question to you, and most of you picked this amount, so I'm going to use this amount. Most tables I saw got to 0.10 grams. Whether you added or took paper away, that's the number that most tables got to. If you got to one of these, that's fine. I just wanted this ending here. So my question is the following. Did that 0 matter? Is that part of the measurement of the paper?
Yes.
That is 0.10 and not 0.11.
Yeah.
Yes. The 0 matters. Oh boy. And the 1 matters?
Yeah.
But the 0 over here don't matter.
No.
So this has what we would call 2 significant figures in the measurement. And so what that teaches us is that zeros at the end of the number are significant because they're part of the reported measurement from the utility you're using. They're part of your reported measurement. They are significant, but there's a caveat. Caveat means there's a if. If there's a decimal. So if there's a decimal, like there's a decimal, it's significant. It's significant. So are significant if there's a decimal. So that's why we say it's yes. This is rule 4. All right. What do you mean if there's a decimal? Would there be a scenario where there's no decimal? What does that mean? Why does that affect things? This class is crazy. Lesson 1. Wait for it. I'll explain it. I'll give you a frame of reference. I'm moving forward in about 20 seconds, just so you're aware. I like to give you that heads up. We've still got 2 more rules to follow. That's crazy. What other numbers could we be looking at? We've looked at 1 through 9. We've looked at zeros in the front. We've looked at zeros in the middle. We've looked at zeros at the end. What else could there be? Here we go. The next one. And this is by far the most complex. I will do my best to simplify it. This is the most complex to understand coming into the class usually. Rule 5. Zeros that are at the end of numbers, reported measured values, aren't significant when there's no decimal. What does that mean? There's a difference between 10,000 versus 10,000. What? And I'm going to explain the difference. I'll explain the difference. There's a difference between 10,000 with a decimal versus 10,000 without a decimal. And I'll tell you what the difference is. In this class, it is assumed if there is no decimal and the number at the end of zero is 0, you have this. Does anybody know what that is?
Oh, approximately.
Approximately. So this little sign here in math means approximately. We actually don't use it in science. We're lazier than that. We just don't put the decimal if it's approximate. So without the decimal, it means that this is rounded or approximate. Whereas if there is a decimal, what that means is that it's exact. So that's why you want those examples there. Just to give you an example that's not science related, that most of us can relate to, money. Most of us can relate to money. Adults, like myself, have many bills. We have money that comes out of our bank account, money that goes in. And on any given day, I may not know until I check my bank account how much exact money I have. But I should know around how much money I have. So if I say, oh, I think I have around $10,000, that's this. Whereas if you have, and you know for sure you have exactly $10,000, that's this. So my question to you then is, how many significant figures is in 10,000 with a decimal? How many of these values matter? Does the 1 matter?
Yeah.
Does all of these 0 matter?
Yes.
So this would be 5 significant figures. By the way, when you're answering questions, significant figures, that's a lot of letters. That's a lot of writing. And most science teachers that are like myself don't like to write that much. So we cut it short. And we either write 5 sig figs, you can write it like that. And that's using the first syllable of each word when we don't want to write the whole thing. We can even be lazier than that. We can write 5 SF. And it communicates the same thing. So if you want to, you're allowed. You can write 5 SF on your test. You don't have to write significant figures every time. Please don't. Your hands are going to start to hurt. So when you're answering for significant figures, just write either sig figs or SF. Usually I write sig figs, but you can also do SF. Right, 10,000 here with no decimal. How many significant figures?
1.
1. Because either all of these zeros matter or none of them. So this is 1 significant figure, or I'm just going to say 1 sig fig now because you know what I mean. Only the 1 matters. There's one more. I wonder what it is. I know what it is, but what could it possibly be? We've addressed pretty much every scenario we can even think of.
Decimal dot?
We have 2 situations that are strange, and I'm going to address those situations. There are 2 situations, and the purpose of significant figures, by the way, is to learn how to round properly. When you're doing measurements and you're doing calculations, how we round properly is through usage of significant figures because it gives us the correct level of precision. So that's why we use significant figures. So there are 2 cases that we do not use numbers for significant figure calculations. And so we say that those values have unlimited significant figures, and that's the final rule. Rule 6. If you count an amount or you have a conversion factor, you have an unlimited amount of significant figures in those values. And so I'll explain what that means in a little bit and give you some examples, but I'll let you write it down first. counted values. What do I mean by that? There are, I believe, 25 students in this class period. There are 25 students. So that's actually not a measurement. That's a count. Why is that not a measurement? A measurement can keep going, meaning, can I possibly have 25.4 students in this classroom? Okay, because a measurement has like a amount you can measure and it has cutoff points and you can make estimations. No, you either have a person or you don't, right? So therefore, anything that we count, an amount of an object like cell phones, calculators, whatever, if I counted to get that amount, it actually isn't a measured value, not measured. And because it's not measured, it's not included for significant figure calculations, meaning the way that they say it is it's an unlimited amount because you don't use it to round. If you don't like writing a lot, instead of writing unlimited, you could write this. Anybody know what that means? Infinity. Infinite amounts of significant figures. Basically, disregard, disregard. And the other one, conversions. You're going to learn conversions. You were supposed to learn conversions at some time in your life, typically in 5th or 6th grade, and again in 7th or 8th grade. This is the class where we use conversions all the time. So we will get to conversions in this class, but not yet. Don't stress it. However, you need to know if you have a conversion. These are established values. 60 seconds in a minute, 60 minutes in an hour. Because they're not measured, they're established. This is equal. They just don't count for significant figures. They're not a measurement, and so they don't count. And so if you see a conversion factor, you just say unlimited or infinite amount of significant figures. It's not utilized for rounding. For now, that doesn't mean much to you. It will later on when we learn how to do calculations with conversions. So the last slide we're going to go to is the next one. And on that one, we're going to look at practice questions together on this. Like, how do we apply the rules to different questions? Hopefully, we've spent enough time with demonstrations to help prove why the rules are what they are, and you can solve these pretty quickly. We're going to go through these set of practice questions together. And then afterwards, I'm going to give you the assignments for the day so you know what to do. I've already posted on Google Classroom like a to-do list for you so you know what you got to do. But I'm going to explain it after we do the last set of practice questions together. Moving forward in 20 seconds. Once again, you do not have to write everything on the slides. If you want to go back to fill in additional information, I am posting it after school. This is the last set of practice questions. You should write them down. I'm going to pause to give you some time to write them down. If you want to work ahead of me, feel free, as always. The question on the board, and this is the type of question you see on your first quiz, how many significant figures are in each measurement? The question is, how many? Meaning you give a numerical value. Are one of these digits significant? Are 2, or 3, or 5? That's how you're going to express your answer. So write these out. If you would like to work ahead of me, please do. You can also wait for me, and I'll go over the answers. And once we finish this slide, we're actually officially caught up with the A days. So we'll be able to participate in the same lab. I'm pausing to give you time to write it down and work ahead of me.
So you're going to teach scientific notation?
Yes, I believe that falls into next class period. Measurements is a multi-day lesson. And is not something that should be rushed through. Because if I didn't take the time, most students get very confused on significant figures if I don't take the time to go over it carefully. One more minute and then I'll start to solve them. How many significant figures do you think A has? Does the 1 matter? Yes. The 2?
Yes.
The 3? 1 through 9 always matters, right? So the answer here is 3. So you can either say 3 sig figs or 3 SF or just 3. I'll get what you mean. All right. That one I hope was straightforward. B, we've got our first scenario with 0. Do the zeros here matter? Yes. So how many total significant figures are here?
5.
5. Okay, so that one is also not too crazy. Oh, I see why someone asked. The C has scientific notation, doesn't it? That's wild. So we're officially going to go over scientific notation next class. But just so you know for now, the whole purpose of scientific notation is to hold how large or how small a number is. So when you're looking at a measurement and you have scientific notation, all you simply have to do is look at the number in front of the scientific notation. You don't look at the times 10 to the 4th because that just holds how large or how small the number is. If you wanted to, you could evaluate it. You could do 9.8000 in your calculator times 10 times 10 times 10 times 10 and look at it that way. Either way, these zeros are in the back. There's a decimal. Do they count? Were they written on purpose? For sure. So this is 5. You don't look at the 10 to the 4th part at all. However, if you had evaluated it, you would have come up with 98,000 if you changed it out of scientific notation. It would still have the decimal because it had the decimal here, right? So it is 5. It's exactly 98,000. Does that make sense? D. 22 meter sticks. To give you context, I had this ready. This is a meter stick. If I gather 22 of these, I have 22 of these meter sticks. What is the amount of significant figures? Very good. Infinite. Because we counted to get the amount. We counted objects. We didn't measure a length, a mass, a volume. We just counted an amount of objects. The answer is infinity or unlimited. This is rule 6. Because it's counted, not measured. Any counted amount, you can't have 22.1 meter sticks or you have a very broken meter stick. If you have 22.1 people, you have a very broken person. Counted, not measured. E. This one, in the past, most students have found this scenario to be the most difficult out of the options. Also the one we just looked at. How many significant figures do you think are in E?
4.
No, not 4.
It is 4. It's 4. Let's evaluate.
Oh.
We know these. So we've got this situation. We know that these aren't actually measured. They're not part of the measured length. But this is because of the activity we did with the scale, right? So 4 sig figs. All right, final one, F. The same as this, except there's one slight difference. There was a decimal here. There's no decimal here. Answer is 2. The 9 and the 8 count, but the rest are assumed to be estimated numbers. So 2 sig figs. All right. So what we learned today was how to determine in a measurement if the measured value is significant or not, and how to calculate percent error. Obviously, you need to practice. So I'm going to go ahead. I'm going to leave this up for just one more minute, and then I'm going to show you on Google Classroom where your assignment on significant figures is and how to submit it. In the other classes yesterday, some students did it in 5 minutes, because it's just basically a bunch of questions like these. So let me know if I'm good to exit out. Everybody good? Need a little bit more time? All right. I have to exit out to be able to explain your assignment. So I'm going to go ahead and exit out. I'm heading to our Google Classroom and our classwork tab.
Wait, miss.
Yes.
If you write on a paper, does it make it heavier?
Because your pencil is made of graphite. Graphite is carbon. carbon has mass. Yes. Okay, so let me get your attention so I can explain the homework you have for classwork homework, because I do believe you'll be able to finish at least one of these assignments before you leave today. The first one is on Google Classroom. It is at the following link. This specific resource is called Science Geek. It was made by a chemistry teacher, and unfortunately, it doesn't link your grade automatically to Google Classroom. So you are going to have to screenshot your grade once you've completed it. After you complete all 20 questions, as long as you got an 80% or higher, I give you 100% in the grade book. So how does it look? Let's take a look real quick. This is what the assignment looks like. The rules are on the side if you need to relook at what the rules are. And you have an example here. It says 0.0040 kilograms. How many significant figures is 0.0040 kilograms? We know we start at the 4 and the 0 after that significant. So the answer here is 2. So we're going to put in 2. See if I can type it. And then I hit check. It tells you correct. Your score is 100%, but you've only completed 1 out of 20 questions. So what I'm looking for is that you completed 20 out of 20 questions, and your score at least says 80% or higher. When you have done this, you're going to take a screenshot of your screen, including the date and time. The date and time and what's here on whatever your screen is. If you prefer, you can take a picture with your phone. Then you're going to go back here, and you're going to attach a picture or the document with your screenshot. If you need help with that, let me know. This is due Monday night. That's the first part of your homework.
Can you do it as many times as you want?
That's a great question. One of the reasons I picked that resource is if you don't get an 80% on your first attempt, you could just refresh the page and do it again. My goal is for you to master the material. If you don't get it right on the first shot, it just means you need more practice. So the second part of your homework is on paper. This is for percent error. This is going to be due at the beginning of next class. So it's 5 questions on percent error. I'm passing them out to everybody now. You learned 2 things today. And so everything to do is here. Your lab safety contract, you've got to get that signed by yourself and a guardian online by Sunday night. The significant figures homework is online, and this is on paper. You're welcome. You can get started with it now. You've got about 9 minutes left in class. So I'm pretty confident you can finish these significant figures part of the assignment while you're here.
Look, it is so complicated.
One on one.
Where's
It's different topics.
option? Wow, that's a lot.
So there's 2 different topics. The one online is significant figures, the one on paper is percent error.
Why do you explain to me? We really swapped our computers. Sarah, I've had exact computers this whole time.
Wait, what period are we going for? Wait, what?
Swap computer. No. This. That exact time we had swap computers. Because he said, wow, my computer like forgot everything. All of mine like shortcuts and everything. Because we had each other. And he gave
And I think I had one of those too. Because I don't have the same one. And I don't have my bookmarks.
Oh yeah, me neither. Wait. Oh my
Alright,
gosh.
let me-
I know it's fine. You go.
If you need help with attaching the screen capture, let me know and I will come around to assist. I'm also at this time starting to set up for the next class period. Yes, how may I help?
Like we take a picture.
Yes, and then just attach it online through the Google Classroom on
You
your
want
phone.
the date and the
The date and the time, like the date and the time and score. After you finish the 20 questions.